Right? Yeah. So yeah, you guys have seen about number systems and codes in our last class, right? For 301 students, and this class we are going to see about digital electronics, right? So I have sent the same link to 1G students as well, right? This is one chapter for you as well, right? So I think, oh yeah, you have one more chapter, right? We have, oh yeah, this is the last chapter. In this we have two I have divided it into two different sections, right? First one is combinational logics and the other one is sequential logic, right? So first, yeah, we'll briefly have an introduction, right? Digital electronics, right? Digital electronics. Can you see this one? Yes. Okay. So yeah, basically we can divide the signal into two different categories, right? The first one is analog signals or analog quantities, right? So something like this, right? Right. So what analog means is analog signal is a continuous signal, right? Continuous signal for any time t, right? See, you have a value. For example, t could be any values, right? It could be 0.1 second, root 2 second, 1 second, 5 second, 10 seconds, 22 seconds, or whatever, right? For any value of t, you have a continuous change in the magnitude, right? Which is called as a continuous signal or analog signal, right? It could be a periodic signal, which is this one, right? We call it as sine wave. Right? Okay. Right. Sorry, guys. Right. So these all called as analog signals, right? And these are called as periodic signal, right? It repeats. We have seen a lot in this in our first chapter, right? And the second category is discrete signal, right? Discrete signal is something like this, right? It has discrete value. The magnitude is not continuous, right? The magnitude is not continuous. It has discrete value. For example, it could be either 1, 2, 3, something like that. There are no 1.5 or no 2.5, something, right? So these signals are called as discrete signal, right? So where your amplitude is not continuous. Here, your both time and amplitude, of course, time is always continuous, right? Here, your magnitude is continuous. Okay, make it as A, right? It could be 0, 1, 0.1, 0.01, point whatever, right? But in this one, in discrete, the magnitude is not continuous, right? They have discrete values, right? There are no 2.5, no root 2, no 2 point, no 1 point, no 0.5, right? Okay, right. So this is called as discrete. And also we have another type, which is digital signal, which is a special type of discrete signal, which has only two levels. One is 1, the other one is 0, right? Digital signal is a special kind of discrete signal which has ones and zeros only. It could be something like this, right? It has two levels. One is 0, the other one, sorry, one is 1 and the other one is 0, right? Discrete signal have magnitude discrete, right, values where only two levels, right? There are no 2, 3. Then this signal is called as digital signal, right? Digital signal. right? So from this, we can understand that digital signal is a signal which deals with only two levels. One is 1 and 0, right? We can represent 1 by the presence of voltage. Presence of a voltage. And then 0, we can assume it as 0 voltage or absence of voltage, right? Right? Absence of voltage. For example, if I have a 5 voltage, right, I can call it as 1, and then if it is a 0, we can call it as ground, right? And we have a threshold value, right? We cannot always have exactly 5, right? So we have a band which is above 3.5 voltages, right? Not all the time. This is not all the, correct for all the conditions, right? 3.5. This is always call it as 1, and below 1.5 we can call it as 0, right? So above 3.5, let this be voltages, right? Voltage, 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 right? This intermediate stage is a non-defined value, right? You cannot have any, or you cannot define whether it is 1 or 0. But if it is above 3.5, we can call it as 1, and below 1.5 voltage, we can call it as 0, right? For a generalized aspect, right? This could vary with your applications, right? This can change based on your application, but it depends on the device design as well, right? You should design it accordingly, right? Okay, so that's a basic of, or kind of an introduction on sorry, yeah, thank you, right? Introduction on digital electronics. Now we'll see about an algebra, right, which is Boolean algebra. Right? Boolean algebra is actually a set of, or special set of laws which can only be applicable to digital signals, right? Which can only applicable to digital signals, right? So here we have only two variables, right? We have only two variables which are 0 and 1. For example, in real life, right? If we have a variable x, it could be from minus infinity to plus infinity. Any values from minus infinity to plus infinity. Am I right? Right. If I say that it is a digital signal, x could be either 0 or 1. Right? If it is a single bit variable, it is 0 or 1. Right? There are no other values. Clear? Right? So it's easy, right? In this algebra, we have only zeros and ones, and it is pretty simple. Right? We have some operators, right? First, we'll see how we can apply the operators in Boolean algebra, right? First one is the AND operator. Right? AND operator is actually can be denoted by a single dot. Right? So what I can do is, for example, 0.0, 0.1, 1.0, 1.1. This you can assume it as just multiplying it, right? Just multiply it. 0.0 becomes 0, 0.1 is 0, 1.0 is 0, but 1.1 only become 1, right? Similarly, we have an OR operator, right? Which is, sorry, a plus, right? Which is, right, a plus. So 0 plus 0, 0 plus 1, 1 plus 1, sorry, 1 plus 0, 1 plus 1. Right? So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 1. Here, right, in binary number system, we have seen that 1 plus 1 is 1, 0, right? But in Boolean algebra, a high voltage plus a high voltage, right? For example, a high voltage plus another high voltage becomes 1. It is not 1, 0, right? This is the special conditions for Boolean algebra. And we have another operator which is not. As I said earlier, we have only two variables. So I can say that 0 bar or 0 not 0 becomes 1, and 1 bar becomes 0. Again, if you have double bar, you can remove them, right? 0. Double bar becomes 0. 0 double bar means you can simply remove that double bar, right? If you have even number of bar, you can simply remove it, right? Also, we have a set of similar to our algebra, we have some um, laws, right? The first one is, right, identity law, which is, for example, consider a number, right, which is 1 dot a will be a. Am I right? 1 dot a will be a. Again, 1 plus a becomes, right? If you have 1 plus a becomes 1, because if a is 0, then 1, a is 1 also, 1 plus 1 becomes 1. Similarly, 0 dot a equals 0. Am I right? It could be either 1 or 0. A could be either 1 or 0, but my result is 0. Again, a plus 0 becomes a. Am I right? Because a plus 0 means if a is 1, 1 plus 0 becomes 1. A is 0, 0 plus 0 becomes 0, right? So my results is the same as your the previous value, right? The next one is a dot a, right? You can see that 1 dot 1 is 1, 0 dot 0 is 0. So I can say that a dot a becomes a. Am I right? A dot a becomes a. Similarly, a dot a bar becomes, if a is 1, then a bar is 0. Am I right? If a is 0, a bar becomes 1. Then 1 dot 0 or 0 dot 1. At both cases, a dot a bar becomes 0. Similarly, a plus a bar, right? It could be 1 plus 0 or 0 plus 1. At both cases, my output is 1. Clear, right? We have a commutative law here as well. For example, a dot b is equal to b dot a. Similarly, a plus b is equal to b plus a, right? And the associative law as well. We have the associative law as well. For example, a dot b into c equals a into b dot c, right? And then this, oh sorry, this is correct for the other way around as well. A plus b plus c is equal to a plus b plus c, right? And then distributive law as well, right? Distributive law also correct, right? This is with okay, I can write it as this one, right? I can say that if a, right, plus bc, remember a plus bc, I can write it as a plus b and a plus c. See here, I have only a this side, and bc means I can divide them into two separate ones, right? Okay, let's see how we can derive this one, right? For example, I'll take my right hand side, and then I'll prove my left hand side, right? So just forget about this one. So what I can do now is, right, so my okay, I can multiply this one, right? So a, right, so it becomes a dot a plus a dot c. Clear. Again now, plus a dot b plus b dot c. Am I right? Clear. Am I right? So I can say that a dot a, I can write it as a simple a, or what I can do is, this will be a plus AC plus AB plus TC. Am I right? So look at here, I have A in these three. What I can do is I can take A as common. This becomes 1 plus B plus C plus BC. What is 1 plus A? Becomes 1, right? So 1 plus B plus C becomes again 1, whatever the value here, right? So I can write it as A plus BC, which is equal to this one, right? So this is how simplifying Boolean equations. You must know A dot A is A, and then 1 plus anything becomes that one, right? So this becomes 1. 1 plus B plus C plus D or whatever becomes 1. Clear? Right. Now we'll see another rule. Yeah, that's true, right? So yeah, the absorption law as well. It's correct, right? So A into A plus B is equal to A. Am I right? How comes? I can do this one, right? A dot A plus A dot B. I can write A dot A as A plus AB. And then now I can take A common, 1 plus B. This becomes 1, and then A dot 1 becomes A. Clear? 1 dot 1 becomes B. That's it. And then, oh yeah, of course, A plus AB becomes A plus AB or A plus B, AC or whatever becomes A. Right. And also, yeah, okay, and A plus AB is also A, right? So I can take A common, so this becomes 1 plus B, which is 1. So I can write my answer, right, which is directly A. Right, I have another law called, which is an important law, De Morgan's law. De Morgan's law, right? What De Morgan's law says is A, B bar can be written as A bar plus B bar. I'll tell you a shortcut, right? So I could write this as A dot B bar. Am I right? A dot B the whole bar. Just remember, if you have dot bar, then that becomes plus, plus bar becomes dot. Just a shortcut, right? Just a shortcut. Dot bar becomes plus and plus bar becomes dot. What you have to do is you need to drop the bar to each elements in the equation. Right? For example, if it is A plus B bar, then I can write it as, yes, first A bar, and then plus bar becomes dot, and then B bar. Clear. Similarly, if I apply De Morgan's theorem to A plus B bar whole bar, clear. I can write it as, first I'll put the bar on A, so which becomes A bar, and then bar on plus becomes dot, and then the bar on B bar, which becomes B double bar. Right? B double bar is actually B, right? I can write it as A bar dot B. Clear. So this is the basic rules, right? Basic rules you need to know before you are going into digital electronics, right? So we have seen about operators, right? And then we have seen the Boolean algebra, right? Of the basic rules, basic set of rules, and how to simplify the equations, right? We'll see more examples when we are doing the tutorials. Right now I'll try to cover the theory section, right? So we have, as we seen earlier, we have seen about operators, right? And also we have some special circuits called gates. We have special circuits called gates to perform these operations, right? Digital operation. For example, to perform not operator, we have a NOT gate. Right, the circuit symbol of a NOT gate is actually a triangle with a right. So if this is A, then we know that A bar, right? Because we know that a NOT operation have only one input, right? NOT operator have only one input. And then we can write a table with all the possible inputs and possible outputs. Input, output. Right, the table with all the possible inputs and output is called as a truth table. Clear? For example, let be A and output Y, which is A bar. This is Y, right? We can take it as Y, which is A bar, right? So input could be, if it is a single bit, as I said earlier, we have only two options. If I have one variable A, it could take only two values. It could be either 0 or 1. Clear? The output will be, if A is 0, A bar becomes 1. If A is 1, A bar becomes 0. Clear? So this is the circuit symbol of the NOT gate, and this is the truth table of the NOT gate. Clear? The truth table is a table which consists all the possible inputs and outputs. Right? Now, yeah, we'll see the next one, right? The AND gate. Right? The AND gate. Right? As I said earlier, we have seen that the AND gate, actually we need two operators. Am I right? Two variables. Right? So I can write it as, or I can draw the circuit diagram, which is AND in the shape of a D, right? In the shape of D, and A and D. I have A and B, which are two inputs, and my output Y will be A plus B. Sorry, if it is AND gate, no, that should be Y equals A and B, A dot B, right? A and B, right? So Y equals A and B. Then let me draw the truth table. As I said, this is my input, this is my output, which is Y, and then I have two inputs here, right? One is A, the other one is B. I have two inputs here. One is A and the other one is B. Then I need to write all the possible combinations of inputs, right? So the first one is 0, 0, 0, 1, 1, 0, 1, 1. Since there are two variables, only four combinations. Look at here, in our last class, we have seen how to write these digital sequences. It could be 0, 1, 0, 1 for B, 0, 0, 1, 1 for A. And if you have another one, that becomes 4 zeros and 4 ones, right? And then output Y is actually A dot B. 0.0 is 0, 0.1 is 0, 1.0 is 0, and 1.1 becomes 1. Clear? 1.1 becomes 1. The third operator is actually the OR operator, OR gate. Similar to the AND gate, we have two, so it is kind of a crescent shape, right? Not like a D, right? You will have a curved structure. It could be A and B, Y, which is A plus B, right? A plus B. Let me draw the truth table. As I said earlier, I have two inputs, A and B, and my Y is equal to A plus B. Right, so since I have two variables, it would be 0, 0, 0, 1, 1, 0, and 1, 1. Right, 0 plus 0 becomes 0, 0 plus 1 becomes 1, 1 plus 1 becomes, 1 plus 0 becomes 1, and 1 plus 1 also become 1. Right, so this is my NOT gate. So these are the three basic, I forgot one. Right, we have another gate called exclusive OR gate or XOR gate, right? XOR gate, right? Exclusive OR gate, right? Exclusive OR gate is actually differs only at 1-1 combination, right? As I said earlier, this 1-1 combination differs from your binary arithmetic. Here we have exclusive OR gate, which the symbol is actually a double curve structure, something like this. A, B, and the symbol, the notation is actually A plus B, or A XOR of B. Clear? Y equals A XOR of B. The truth table is actually A, B, and Y means 0, 0, 0, 1, 1, 0, 1, 1. Right? For exclusive gate, it will be 1 only if, right, any the other one, right? For example, this should be 0, then 1, 1, but when it becomes 1, 1, it becomes 0. Right? It becomes 0. So we can write it as Y equals A XOR of B, which is equal to A bar B plus A B bar. Clear? This is 0, so I note it as A bar, and this is 1, so I wrote it directly B, and then here A, and then this becomes B bar, right? The bar is on the other values, right? So I can directly write it as A XOR of B. If I have a format something like this anywhere, I can directly write it as A XOR of B, right? So this is how we can generate a Boolean function, right? A formula from a truth table. We need to select the ones and then write down the equation for the ones, right? A0 means A bar, B1 means directly write it as, and then put a plus A1, so put it directly, and B0 means just put a bar there, right? That becomes A XOR of B. Now we have 3 more combination gates, right? We have 3 more combinational gates. First one is actually NAND gate. NAND gate is actually a combination of a D or AND gate and a NOT gate. Right, this could be A, B, and this will be A dot B bar, and this will be, sorry, this is A dot B, and this will be A dot B bar. Clear? If I draw the truth table, A, B, A dot B bar, right? This will be my Y. This is A dot B, and hence I have a NOT gate that becomes A dot B bar, right? This could be 0, 0, 0, 1, 1, 0, 1, 1. Clear, right? So 0 dot 0 becomes 0, and then 0 bar becomes 1. 0 dot 1 becomes 0, and then 0 bar becomes 1. Similarly, this one also 1. But 1 dot 1 becomes 1, and 1 bar becomes 0. Clear? Right. Similarly, we have NOR gate. Right. NOR gate is a combination of OR gate and a NOT gate. This is A, B. This will be A plus B, and this will be A plus B bar. If I draw the truth table, A, B, and Y, 0, 0, 0, 1, 1, 0, 1, 1. Right, so now this will be A plus B bar. 0 plus 0 becomes 0, and 0 bar becomes 1. 0 plus 1 becomes 1, and 1 bar becomes 0. 1 plus 0 becomes 1, and 1 bar becomes 0. 1 plus 1 again become 1 and 1 bar becomes 0. Clear. So this, what we can do, sorry, we can simply draw the circuit diagram. Instead of a NOT gate, I can put a small ring in front of it. Right? This will be your NAND gate. Right? For NOR gate, the same thing. So whenever you have a ring or a circle, you can say that there is a invisible NOT gate, right? Even in sequential, and we'll see it later, right? So this will be your NOR gate, right? OR plus NOT becomes NOR, OR plus AND becomes, sorry, NOT plus AND becomes NAND. Similarly, we have X NOR gate as well, right? Exclusive NOR gate. X NOR, right? The structure is actually, as we seen earlier, right? So we see in the truth table, which is A, B, right? This is A XOR of B bar, am I right? Which becomes A X NOR of B, right? So I can write that for XOR flip flop, sorry, XOR gate 0 0 0 1 1 0 and 1 1. Am I right? For XOR gate, without this 0, see here, I had 1, sorry, 0 1 1 0. What I need to put here is just put a bar there. So 0 becomes 1 and 1 becomes 0. 0 becomes, sorry, 1 becomes 0 and 0 becomes 1. Or in simple words, I can say that A X NOR of B is equal to A bar B bar plus A P. Clear, right? So let's see how we can derive this one, right? So as we know that, let's say, okay, look at here, right? So Y equals A XOR of B means I can write Y equals A B bar plus A bar B. Am I right? A B bar plus A bar B. Now Y bar, which is A X NOR of B, am I right, will be A B bar plus A bar B whole bar. Am I right? Now let me expand it, right? So A X NOR of B can be written as, so I'll put the bar first, so I can write it as A B bar bar and plus becomes dot and then A bar B bar. Clear. Right now, again, I'll put the bar, right? I'll apply De Morgan's theorem in first and 1 and 2, right? This one and this one. First, let me remove the bar. So A becomes A bar and dot becomes plus, and then B becomes B bar becomes B double bar, which is B. Am I right? And then dot, right? There are no bars into the dot, so that will become the same. And then A double bar, which is A plus B bar. Now just apply the distributive law. We can multiply it, right? So A bar, A B, right? I can write it as A bar A plus A bar B bar, right? A bar A bar B bar plus A B plus B B bar. We all know that A bar is 0. Am I right? If A is 0, A bar is 1, and A is 1, A bar is 0. So at any case, either one of them, either one value will be 0. Hence, the multiplication is also 0. So I can say that this is 0. Again, B dot B bar is also 0. So I can write it as A bar B bar plus A B, right? Which is the same thing, right? So right, so we have verified that A bar B bar can be written as A B bar using simple Boolean expansion and applying Boolean functions. Right, now let's see how we can build digital electronic circuits, right? How we can build digital electronic circuits, right? For example, the question is, I'm asking you to build a single bit adder, right? We'll start from single bit adder, right? Single bit adder, also called as a half adder, right? A half adder. So as I said earlier, when I am adding two bits, right? So if I add 1 plus 1, right, that becomes, I will have a sum which is 0 here, and also I will have a carry which will be bring to the next level. Am I right? So when I am adding two single bits, I will have two outputs, right? Whenever you are designing a digital electronic circuit, you must draw a truth table which consists all the possible inputs and possible outputs, right? It could be zero or don't care, whatever, but your truth table must consist all the possible inputs and outputs. In this case, when I am adding two bits, I have two outputs. One is sum and the other one is carry, C, right? So for example, if I going to add two bits, right, A and B, I am going to have two outputs, which is sum and carry. Am I right? So this will be my input. This will be my output. Right? As I said earlier, I have only two variables, so it could be 0, 0, 0, 1, 1, 0, and 1, 1. Right? 1, 0, and 1, 1. So now let me put the sum first. Right? So we'll do it. 0 plus 0 is actually, if it is 0, 0, I could say that the sum is 0. Also, the carry is also 0. And I have nothing to carry, so I can make it as 0, 0. If it is 0 plus 1, of course, sum is 1, but my carry is again 0. 1 plus 0 is again the same thing, 1 and 0. But for 1, 1, what I am doing is my sum will be 0 and my carry to the next level will be 1. So I could say that my sum is 0 and carry is 1. Right, so this is the truth table of a half adder. Right, now the next thing we need to do is we need to write the Boolean equation or a Boolean expression for both sum and carry. Right, okay, for sum, see here, just choose the ones. I have only two ones for sum, am I right? And then apply the Boolean naming. If I have 1, then that 1 is happening when A is 0 and B is 1. So I can write it as this section, right, is as A bar B. This as A is 1 and B is 0. So I can write it as A B bar. Right, so I can say that my sum is actually, right, this one and this one, right? So A bar B plus A B bar. What is this one? A bar B plus A B bar. We have already seen, right? A bar B plus A B bar becomes A XOR of B. Right? A XOR of B. Similarly, we need to do the same thing for carry. Look at here. Carry has only one, which is at both A and B equals 1. So I can say that my C or carry is equal to A dot B, which is an AND gate. Right now, I need to design the circuit. Right? I need to design the circuit. Right? For my sum, so I have inputs which are A and B. Am I right? And then my sum is actually A XOR of B. What I can do is I can take both together and an XOR gate, right? An XOR gate. This will be my sum. And my carry is actually A dot B, which is an AND gate, right? I can put a circle and another circle and an AND gate, and this will be my carry, right? So if I design a circuit something like this in a box, right? The whole thing will be in the circuit, and whatever the value we are giving, the circuit will give you the digital outputs. You can design the circuit in electronic workbench and you can verify the outputs as well. Clear? You can design it and you can verify the functions, right, using electronic workbench, right? If you have any doubts in doing that, you can always contact me. Okay, right. So now, yeah, we'll see a bit advanced thing, right? Maybe, yeah, always the next thing it will be a full ladder. A full ladder. Full ladder is nothing but adding 3 bits, right? So for example, as we did earlier, when I'm adding 1 0 1 1 plus 1 1, what I did is I add, even though I am adding 2 numbers, so 1 plus 1 becomes, yeah, my sum is 0, but I need to take a carry to the next level, right? So now to perform this level, I need to add 3 bits. Am I right? This one, and this one. I have to add my carry A and B. Am I right? So that becomes 1 1. So 1 is my sum and another one is my carry. So this becomes 1 and 1. Clear? Even though I am adding 2 things, I need to perform a 3-bit addition in the middle, right? Hence we call it as a full ladder, right? So as I said earlier, we have 3 inputs in this case, right? So which one is A, B, and we make it as carry in. Carry comes in. And similarly, I have only 2 outputs, which are sum and carry out. Carry, which is brought to the next level. Now, let me put the combinations, right? Could be 0, 0, 0. Okay, I'll put it, right? 0, 1, 0, 1, 0, 1, 0, 1. Right? Again, 0, 0, 1, 1, 0, 0, 1, 1. 0, 0, 0, 4 zeros and 4 ones. My table is complete. Right, now let me perform the sum and carry, right? So 0 plus 0 plus 0. So easy. My sum is 0, carry out is also 0. Next one, 0 plus 0 plus 1. My sum is 1 and carry is 0. Again, 0 plus 1 plus 0, my sum is 1 and carry is 0. Here, when it becomes 0 plus 1 plus 1, of course, my sum will be 0 and carry will be 1. Again, at this combination, again, only one, I have 1 plus 0, 0. So sum will be 0 and carry will be, sum will be 1 and carry will be 0. Here I have 1 plus 0 plus 0, which is 0, 1. 1 plus 1 plus 0, again 0, 1. At 1, 1, 1 combination, I will have my sum as 1 and carry as 1 as well. Right, now we need to write down the equation for sum and carry separately. Right now, let's take it as for sum. Sum, I have only 1, 2, 3, 4, right? So this is this sequence, this, and this. Am I right? So look at here for sum, first one, A bar, B bar, C in. That is the only one, right? So I can write it as A bar, B bar, C in. Plus the next one, A bar, B, C in bar, right? B is the only one. The third one, plus, right? Only A has one, right? So A, B bar, C in bar, right? Remember, when you have separate bars and whole bar, it has 2 different meanings, right? That there need to be a break in the middle. You cannot make B bar dot C bar is not equal to BC whole bar, right? And the third one, all three are 1, right? So I can write it as A, B, C in, right? A, B, C in, right? Okay, now let me take this C in here, right? This C in here, right? A bar, B bar, C in, and A, B, C in. I can take C in as a common, no? So I can write it as C in into A bar, B bar plus A, B. Am I right? C in into A bar, B bar plus A, B. Plus, out of these two, I can take C in bar as common. Am I right? So C in bar into this one, A bar B plus A B bar. Clear. Now look at this one. What is A bar B bar plus A B bar? Sorry, A B, which I can write it as C in into A X nor of B. A X nor of B. Similarly, what is A bar B plus A B bar? Yeah, I can write it as C in bar into A X or of B. Right, now look at this whole equation. A, just assume it as capital X. Right, A X bar, A bar X. Again, the whole term looks like the XOR gate. Right, so I can write it as this one as A XOR of B XOR of C in. Clear? Right. Now move to the next one. C out. I have only one, right? 2, 1, 2, 3, 4. This one is actually right. A bar B C in. This one A B bar C in bar. This one A B C in. Oh no, there should not be bar right here. And then this one bar, right? This bar should not be there. When I have 1 0 1, no, 1 0 1 and 1 1 0. For this one, A B C in, right? So I can say that my C out carry out is equal to A bar B C in plus A B bar C in plus A B C in bar plus A B C in. Right, now what I can do here is yeah so A bar B A B bar, yeah, I can take C in common, right? A B common here, right? So I can take it as C in, which becomes A bar B plus A B bar plus I can take A B as common, right? A B as common, which becomes C in plus C in bar. Am I right? C in plus C in bar. What is C in plus C in bar? Which becomes 1, right? If C in is 0, this becomes 1. If it is 1, this becomes 0. Right? So I can write it as C in into A XOR of B right, plus AP. Am I right? Now, what I have to do is we need to draw a circuit to perform these two operations. Right. Oh, sorry guys. Do you have class at 11? You guys have class at 11 o'clock? Okay, I'll complete with this one, right? There is another 5 minutes question, right? I can finish it with another 5 minutes, right? So we can complete this one and we'll move to the next chapter, right? Next slide. Right now, we need to draw the circuit diagram, right? We need to draw the circuit diagram. Sorry. First, look at here. Sum is A bar, B, C bar. Here also I have A bar, B bar, A bar, B bar. Right? So what I can do is I can two different gates, right? I can two different gates. For example, this, let this be my A, B, and C. Right? So I have A, B, XOR gate. Sorry, this will be my C in. Right? And then I have my A XOR of B, XOR of C in. This will be A XOR of B, and this will be A XOR of B XOR of C in. Clear, right? This will be A XOR of B XOR of C in. Now, what I have next is I have C in into A XOR of B, or C in and A XOR of B. Right? I have A XOR of B here and C in here. I can give it to an AND gate, right? Dot means AND gate. And then I also have an AB component, which is this one, right? I put A, B. And that has to be given to another AND gate. And look at here, both are added together. So what I need to do is I need to give it to an OR gate, which is to add these two together. This will be, right, A XOR of B into C in, and this will be A dot B, and hence this will be my C out. The equation will be this one plus this one, right, which is A XOR of B into C in plus A dot B. Clear, right? So yeah, that's all about today's class, and I'll upload a lecture, sorry, a set of questions, right, for you to practice. Okay, right? So hopefully you guys will be here in Jaffna next week, right? Probably from January 15th. I'm expecting to meet you all, and we may have a quick revision, and then we can have our lab sections, lab sessions as well, right? So yeah, that's all about today's class. And first year students will meet you on next Tuesday at 11 o'clock. Right? Thank you. Any questions?